Hey everyone, we're back. So we're looking at another example here. Here I have the SAT scores and ACT scores. I have statistics about them. I have the mean and the standard deviation. And so here are two tests, standardized tests, and we want to be able to compare the two groups. It wouldn't be wise for someone who got a 500 on their SATs to go up to somebody that got a 35 on their ACTs. The ACTs only go up to 36, and say, I scored better than you because 500 is way bigger than 35. So let's actually see how a score of 500, so if x is 500, how does that compare? What score would that be on the ACTs? So what I can do is I can turn this 500 into a z-score. So z is going to be equal to the x value minus the mean divided by the standard deviation. So a 500 on an SATs is far below the average. It's over 2 standard deviations below the mean. And remember, 95% of our data is within 2 standard deviations. So if you're below that, this is an unusual value. Someone getting a 500 on the SATs is unusual. Okay? So what is the score on the ACT for someone who has this z-score? So what I can do is I can sort of do this equation in reverse. So that would be the equation that I have this value is equal to x minus the mean, which is 20.6, divided by 5.2. So how do I solve this equation? Well, I would multiply by 5.2. So I'm going to take this value, I'm going to multiply it. I'm going to take this value and multiply it by 5.2, which is our standard deviation. And then I would add to that my mean. That's how I would solve for x here. And so somebody getting a 500 on the SAT is like somebody getting an 8 or a 9 out of 36 on the ACTs. So someone who's getting a 500 on the SAT should not be bragging that they did better than somebody on the ACT that got a 35, because their score on that scale would be more like a 9. So now let's go the other way. What if somebody on the ACT got the 35? What would somebody taking the SATs have to score to do just as well as this person? So let's figure out what the z-score is for someone who got a 35 on the ACT is. So someone who got a 35 on the ACT is going to be 35 minus the mean of 20.6 divided by 5.2. So someone who gets a 35 on the ACT is unusual, borderline rare. Okay, it's still within 3 standard deviations, so we're okay. But it's outside of the 2 standard deviation ranges, but on the other side of the spectrum. So what would someone have to get over here to match a 2.77 z-score? So that would be equal to someone who has an x minus 896 divided by 174. So I would multiply 2.77 by 174, and then I would add 896. So you'd have to get like a 1380 on your SATs to be matching someone who got a 35 on their ACTs. All right, that was just a fun little exercise. Let's move on to what we're really doing here, which is looking at the standard normal curve. So we've looked at the normal curve before, but now we have the standard normal curve. So the normal curve, the mean could be any mean. And it could be 896 for SATs. It could be 20.6 for ACTs. It could be 68 inches for the height of a gymnast, or 79 inches for the height of a basketball player. That would be in the center, and then we would label 1, 2, and 3 standard deviations above and below that. Now you might want to go back to the video where we did talk about a normal distribution, and we found 1, 2, 3 standard deviations away from the mean, how many data points were in there, and we checked to see that they were following the empirical rule. The empirical rule still holds true. There's about 68% of my data that's within 1 standard deviation, 95 within 2, and then 99.7 within 3, which leaves about 0.3% outside of 3 standard deviations. Now, when we standardize a score, we put it on this standard normal curve where the standard normal curve has the following characteristics. So what you need to know is that on the standard normal curve, the mean is 0, standard deviation is 1, the values along the bottom are z-scores, the area under the whole curve is 1, and when we say 68% of the data is within 1 standard deviation, that would mean in this section right from here to here, this would be 34%, but we would write that as 0.34. The area under the curve right in this section is 0.34, and this section is also 0.34. Below the mean is half the data, so that's 0.5, and above the mean going this way would be another 0.5. Okay, so the graph is symmetric. Again, the left of the mean we have 0.5, to the right of the mean we have 0.5, and then I think that's all you need to know for the standard normal curve. Now, if I wanted to find something that wasn't exactly 1 standard deviation from the mean, now I could figure out the area under this curve, the shaded region in blue. Well, if we know that coming up to the mean here is going to give me 50%, and we know that this part right here is 34%, then 50, so 0.5 minus 0.34, should put an equal sign in there, is going to give me 16%. So this would be about 16%. It's not exactly 16%. There's actually a function that calculates this, and we can use that function. Now, if we have values that are not 1 exactly a standard deviation away from the mean, again, we have a function that will calculate that for us. And we'll look at that in the next video.